Okay, good afternoon, viewers. Let me start this second session for today's lectures. And here it's our pleasure to have Dr. Krishanu Moulik from ISI Kolkata. And he will be delivering one particular talk. And as I know precisely the topic of his particular session, he will of course describe that one, and it's like a choice in the stochastic processes in the application of the urns. So he will deliver his particular talk, and he will be having one more talk in the next few days after. So let me introduce Dr. Krishanu Moulik. He is presently the Associate Professor in the Department of Theoretical Statistics and Mathematics in ISI Kolkata. And he did his B.Stat and M.Stat from ISI Kolkata in the years 1996 and 1998 respectively. And he got his PhD award from Department of Statistics, Cornell University, USA in the year 2002. And his research interests are maxima of random variables, record sequences, multivariate regular variation, asymptotic independence, conditional extreme value model, random recursions, Green probabilities, random sum, urn models, free probability, etc. And he got several awards and honors, like let me just mention few of them. In the year 2015, he got Young Researcher Award from International Indian Statistical Association. During 2008 to 2011, he was an associate of the Indian Academy of Sciences. He got in the year 2008 prestigious award, Microsoft Research Young Faculty Award. In the year 2002, he got Institute of Mathematical Statistics Laha Travel Award. And also he got in the year 2002 Student Scholarship to attend Spring Research Conference on Statistics in Industry and Technology. So these are the few words what I can describe about Dr. Krishanu Moulik. So as I've introduced Professor Moulik, please start your particular session. Thank you very much.
Thank you, Dr. Ghosh, and thank you, organizers, for inviting me. So do I need to keep the video on, or will it cause, I mean, I'm indifferent to it, but it may require more bandwidth. So what would you suggest?
So it's your choice. Perhaps as the number of participants increase, it may have a problem in the bandwidth. So
okay, so maybe I'll
don't having any problem.
I'll just put it off, but before that,
want to demonstrate something over your face or some hands-on figures are required, then of course I think I don't have any problem. That is.
Okay, no, maybe I'll put the video, but first let me see if I can share it properly quickly. Yeah, is a screen visible?
Yes, it's coming. Yeah, now it's visible. Yes.
Yeah. So let me try to make it full screen. Yeah. I was trying to use a different viewer to make it.
Excuse me, I think that the size is getting far bigger perhaps, and only one segment, left-hand side segment is coming with, yeah, now it's okay, now it's okay.
Okay, okay.
Yes.
Yeah, no, I was using trying to use a different viewer so that I could write it on the file, but it seems that Google is not being able to share that. So I'll leave it like that. Can you see the parser, the small hand signal because that will
Yes,
help
yes,
me
it's coming.
to,
Yes,
like
we can follow.
highlight things. Yeah. So thank you once again. And as I have discussed, what I'm going to do over 2 lectures is, so I'm going to, as you can see from the title, I'm going to talk about stochastic approximation today. It's a general method, so which is used in optimizations and many other issues, and it has found application in several other areas. So I'm going to spend much of the talk today to explain what stochastic approximation is. And based on that, what I'll do in my next lecture on Thursday, I'll start describing what an earned model is today, possibly, depending on how much time we have. On Thursday, I'll solve earned model problem using stochastic approximation. So that's my plan. And if we have more time left on Thursday, then we can discuss something more about further about earned models. So this much of the work that I'll be presenting today, it's classical. There was some results towards the end which were taken from our work, my work jointly with Ujan Gangobadhyay to solve the earned model problem. Ujan started working on this problem quite a few years back with me when he was finally a master's student in ISI. Then he carried on this work during his PhD days while he was in University of Southern California. So with that introduction, let me start about stochastic approximation and what stochastic approximation is. So first, let me try to motivate like why someone would try to study a problem like stochastic approximation. So it's an optimized. So one way you can think of it is it comes up, it's through an optimization problem. So suppose you have a performance function that you want to optimize. Let the function be fx, and let the corresponding parameter be x, you want to choose the parameter x so as to minimize fx. And in general, you will be subject to several constraints like qix less than equal to 0. We may not get into that far with stochastic approximation because it will not be exactly required for my analysis of earned models. So I'll put the framework in what I want more. So that's a optimization problem. And now there are like many deterministic ways to solve this optimization problem. And but why do we need to deviate from that? A few of the issues that turn up is that this performance function fx, that may be difficult or the constants may not be explicitly known. They may be quite expensive to calculate. So then you cannot, if you don't know them directly, then you cannot use the classical methods. Or even if you can calculate them, like, I mean, many of the application where they come from some experimental process, reading them, the constraint as well as a performance function will be subject to error. So how do you handle such a system and do the optimization? So one suggestion will be to consider recursive Monte Carlo approximation. So generate, I mean, it's a usual way of optimizing things, but rather than usual optimization, you observe things with randomness, and so you get a recursion, but there will be certain randomness, and you have to take care of that. So that's a recursive Monte Carlo approximation. So what you have is you have xn, which is the estimated optimal value of x in nth step. And instead of, so in the classical setup, you will study f of xn, and based on that, you will update xn to xn plus 1 and hopefully expect the sequence xn will converge. But as I said, the setup that we are considering, that in that setup, either calculating f of xn directly is way too expensive, way too difficult, or the natural setup is such that all the observations will come with certain amount of error. So when I'm in the nth step, my choice of optimal value is xn. Let yn be the corresponding estimated performance value. So yn is not f of xn. It has some error in it, some noise in it, some error in it. So that's why we make a simple additive model that yn is equal to f of xn plus xi n, where xi n is the additive noise at nth step. And what we are assuming is that this noise can depend on not only on xn, but on the entire past. Because I mean, that will be a much more general model, and that will help us more. And these are all these past choices of the optimal value and the corresponding estimated performance values. They are all known. So xi n can be a function of all of them. So this is the model, and then now we need to optimize it. So how such things are generally optimized is that, and I'll show you how we do it. So first of all, xn is interpolated into a continuous time process. And so we'll build a process over entire real line. And then we extract some convergent subsequence. I'll not do the exact details because it will, like too technical. That will be too technical. So I'll kind of explain how it is done. So this convergence, so it will be inside a continuous time process. So we'll use some kind of compactness argument, and then the convergence, and then we'll show that there will be a convergent subsequence of the continuous time process. So it will be either in the Arzela-Ascoli sense, which will be more of the case when you talk about almost everywhere convergence and things like that. But also we'll be talking about weak convergence of probability measures on. So this continuous time process will be obtained from xn through linear interpolation. Very simple interpolation. And then what we'll do is we actually want to study the behavior of xn as n goes to infinity. So I'm sort of like to get a idea. What we are trying to do is I'm trying to bring in extreme rightmost point towards the center. So what I need to do is, if I want to bring the extreme rightmost point towards the center, I should keep on shifting everything towards the left. I mean, obviously the infinity won't budge, but I mean, that's the idea. So it's sort of like you are bringing the right more and more towards the center. Or if you are looking at time zero, since you are making a left shift, so first you observe xn at time zero, then xn plus 1 at time zero, and so on. So eventually, as the situation progresses, hopefully you will, the behavior of this continuous process at time zero will give you the limit of xn. That was the idea. So and and this sort of left shifts are kind of quite well studied object in probability theory. They come up in ergodic theory and many other things. And then you talk about weak convergence, and since the space will be on probability measures on space of continuous functions. Again, there will be essentially an underlying Arcelor-Ascoli kind of argument, and then you will have some tightness requirement, and you will prove something is compact, and then you will show that there is the sequence of probability measures will have a weakly convergent subsequence. So the whole idea is somehow embed the extents into a continuous time process, study the continuous time process, invoke some compactness argument, draw a convergent subsequence, and study the limit of, or the subsequential limit. So what? So the crucial idea, I mean, there are many approaches to it, but one of the approaches that Leung brought in his 1970, he had a bunch of papers with his collaborators during 1975 to 77. As I said, this is a pretty old, but it's still very powerful and useful technique. That he showed that these subsequential limits, sorry, will satisfy certain ODE. I'll show you how does that ODE appear and why should it satisfy that ODE. That will come quite naturally, but checking the details will be obviously require some more work. I'll try to show some of those details in the next lecture. Next day after tomorrow. And so there are several approaches. Obviously, the ODE may not have a unique solution, so it may give rise to a dynamical system. And based on that, a detailed analysis of the stochastic approximation and its convergence can be done. But thankfully for our model, the problem is not complicated. The associated ODE, or at least the R model that we'll be discussing, the associated ODE will have a unique solution. And if the associated ODE has unique solution, then the stochastic approximation will also have a unique solution, and we'll have the corresponding convergence, the unique limit. So that gives you the whole setup in a nutshell. So next, what I will plan to do is I'll show you 3 examples, starting with Robbins and Monroe, who studied it all. But before we get into more specific examples, are there any questions about how one should, about this setup or the broad approach? There is always a problem in this sort of online seminars that you don't get to see your audience. If you have any questions, please stop me, speak out. And if you do a chat, unfortunately, I'm not sure I'm able to see the chat because I'm using a full screen on my laptop, so I won't be able to see the chat.
So I will transfer the questions or queries if there is any in the chat box.
Yeah, that would be nice. If there is somebody writes down the chats, one of you from the organizers, please let me know. Yeah. So now, are there any questions?
Yeah, I've not seen any questions.
Okay, sure. So let's move on to the next slide. So it's a Robbins-Monroe procedure. So Robbins and Monroe, they were the first one to introduce it way back in nearly like about 70 years back in 1951. So what they do is, again, as I was saying, they were observing a process over time and different parameter values. And this process, like suppose it's an industrial process, then it will be repeated over and over again. So when the parameter value is x, the actual process value would be f of x. But as I said, suppose it's an industrial process, it's kind of an output or something. So you won't be able to observe the actual effects, but you'll observe effects plus some error. And this thing will be repeated again and again. So for a given parameter value x, the process may be repeated several times over. And then what you do is you look at the process value for each of those runs for that constant parameter x and take their average. Let's call that y. So y will, that's a natural thing. If you can't see fx, you get some of its realization and you take its average and you use that as a proxy to fx. And we use the usual model that I was suggesting. So when xn is the parameter value, the actual process value will be f of xn, but we'll be observing yn, which will be coming up with an additional error, which I will denote by psi n. And here their aim is to, in the Robbins-Monroe procedure, the aim was to find an optimal parameter level theta such that f of theta is alpha. So that's what they were trying to solve. And in general, that can be solved easily by a fixed point equation. So you look at the corresponding transformation Tx, which is f of x minus alpha plus x, and theta will be nothing but the fixed point of this transformation T. And if you know f, then you know T, and then you can quickly and easily solve for this fixed point. But there are, and so there, as you all know, there are like standard Newton methods when it is non-decreasing and strictly increasing at theta. So look at this form. This form will be very interesting and it will come back to us. So if you know f exactly, then it will be just simply xn plus 1 will be the past t minus something multiplied by f of xn minus alpha. And in this case, xn will converge to theta. This is like classical object. But we won't be able to do it as it is. And the reason is, first of all, as I said, it may be difficult to compute the observed value at different parameter levels. It may be, also it's, even if you can do the simulate, it may be, so what you need to do then, so the theta will be obtained recursively. So whatever be the value of recursion that you get, you have to set up the system to run the system several times at that specific value. And it may not be that easy to calibrate the system at a particular parameter value and then run it several times. Or even if it's possible, it can be way too expensive to perform. And also, like, you have been observing the process with several parameter values and the corresponding outputs. In fact, for each parameter value, several outputs. So you have collected a whole bunch of information, and what you are doing is you are not anything other than this fixed Newtonian idea. So the only way the past is affecting is through xn and f of xn and the corresponding derivative. But the things can be much more, you can use much more information from whatever you have done in past. So that suggests that we do something else. And as I said, here you have the reciprocal of the derivative, and you are sort of scaling your current process value, the difference between your current process value and the target value by that derivative, and then shifting the x appropriately. But rather than getting fixated with this derivative, we'll try to use something more general. And the other reason is, if you get fixated with this derivative, then every time you actually have to calculate this derivative. While you may be able to calculate the function f at certain values, calculating the derivative will be even more expensive. Even if you try to do it, approximate the derivative by finite difference or something like that, it requires more work. So can we put some multiplying factor here, let's call it an, and write it as xn plus 1 is equal to xn minus an times yn minus alpha, something like that. So that was the idea, and that's being done. So ans are called a step size, it's taken to be positive. And here comes a recursion. As I said, the recursion is, so instead of f of xn, I put in f of xn plus zeta n, which is yn, because you won't be able to observe f of xn. That is our limitation. So you'll be observing yn. So this is the new recursion we have, and we would expect that this recursion, I mean, we'll try to put in conditions and prove that this recursion should converge. Here things are random, so in some appropriate sense in probability theory, to the optimal value theta. So that's the Robbins-Monroe procedure, which put conditions on an and analyzes this thing to show that xn converges to theta. So what are the conditions on step size? They do, obviously you cannot put any step size. So it's an has to go to 0. And the reason is the ans are, like getting, they're multiplying with the noise. So ans are, so you have to look at this an times xi n, and this an times xi n should go to 0. So an should kill this noise off. And then if it can kill this noise off, then you should come back into the right setup. So that was the one of the requirements. And the other thing is that some an should diverge. That sort of helps you, as we shall see, it sort of allows you to cover, sweep all possible choices and helps you to converge to the right limit. You won't get stuck at some wrong place. That's the rough idea. So these are the two conditions. Some of the analysis further require that summation an may diverge. It may not be summable. By the way, ans are all non-negative. I already mentioned it earlier here, but I forgot to repeat it. So ans are positive, they will go to 0. It will not be summable, but some people will put the additional constraint that it is square summable. Square summability allows them to invoke some results from martingale theory, because they can construct a corresponding martingale which is square summable, and then square summable martingales have nice properties and they use that. But what we shall show is it's not necessary to assume square summability. Just these three conditions. The 0th condition is an positive, an going to 0, and summation an diverges. That will allow us to get the right result. So Robbins-Monroe would assume that the following condition on noise, that psi n, which was a noise, its conditional expectation given the past is 0. That is, once you know what has happened, and that you know already, so that it's not natural to condition on that, then on an average, knowing the past, on an average, the noises do not add substantially anything. So, and that's a natural thing to assume. I mean, noise shouldn't have a bias. If the noise take you in one direction, then there is something happening. You are not supposed to neglect it as a noise. So noise should be just something which is not, on an average, shouldn't contribute. And if you are familiar with martingale theory, this sort of suggests a martingale type behavior. And that's why this idea to assume an square to be square summable. And then you also assume a square summability on, square integrability on xi n. They together would give you a square summable martingale, and which will help you in further calculation. But we won't do that. And it's immediate to see that what is xi n? It is nothing but yn minus f of xn. F of xn is deterministic given this past history. So note that for x we know until the present time n, but for y we know only until the previous time. So this is what we have. Okay. So any questions up till here? So this is a classical Robbins-Monroe setup. We're not going to get into the details of the proof. We'll do it in for a more general setup. Classical Robbins-Monroe setup, but in general, so xi n is additive with f of xn. So yn equal to f of xn plus xi n. But in many practical situations, more complicated relationship with psi n can be assumed. So in our analysis, we'll still continue to take this additive setup because that will suffice for our analysis of our model. But you can, I mean, different structures are assumed, and so this stochastic approximation is a broad framework, and this is analyzed in different frameworks. So yeah. Now let's connect with dynamical system and its regulation. So here is a dynamical system. So I'm trying to put a more general framework here. So Zn is a dynamical system. And how does it develop? It looks at its current value. You get an innovation xn, and you get some random noise, and they all put together into a function g, appropriate function g, and that gives you the next level of the value of the dynamical system. So xi n will be typically a sequence of noise random variable, and xn is the value of a parameter at the next step, and then is the current value. So what I will assume that if I consider the setup that all the xn's, so there is a fixed number x, non-random fixed number x, and all the xn's are fixed at x. So this dynamical system is being driven by this random noise psi n and the past value, but this xn is staying constant at x for all x. Then it can be on by appropriate assumptions on psi n, the system becomes reasonably stable, and we get the following steady state quantity. So what is this A? This A is, suppose A is some possible state among the in the range of Zn. It's called the error state. So you suppose you want to study that this dynamical system shouldn't get into those error when your parameter is at x. And what is the steady state probability of that? Let's call that f of x. And obviously you want to find out x, which should satisfy that fx is. So given some threshold cutoff for the probability, so these are error probability, so you don't want it to be too large, so you fix a cutoff threshold which you are okay to live with, 5%, 1%, as the situation may demand, and you want to find out x such that f of x is less than or equal to alpha. Again, I mean, if you forget this, everything in the background, again, this is like an optimization problem. And it sounds like what we have been discussing in Robbins-Monroe. And not surprisingly, you can handle it with Robbins-Monroe procedure. So you define Wn to be so it's the indicator function. It's 1 when error happens and 0 when it doesn't happen. And so this tells you whether for that parameter the system is in error or not. So this is so actually whether your parameter leads to an error, that's the actual process value, and this is the observed process value. So that suggests that this should be your Robbins-Monroe procedure. And then you have to show that the suitable conditions on AN should make this xn's converge to the required value of the parameters. So that's an application from dynamical system. And the next example will come from a function minimization. So it was due to, Robbins-Monroe was in 1951. The next year, Kiefer and Wolfowitz had a similar idea, and they were motivated by trying to minimize a function. So I'm doing it for minimization, but you can actually also do it for maximization as well. And they were motivated because, again, this is something which turns up in several setups. So suppose the parameter is x, and the actual process value is fx, and y is the observed average process. So exactly like what happens in the Robbins-Monroe. So and this parameter, suppose that this parameter is in the space k-dimensional Euclidean space. So choose the parameter to be choose the parameter value so as to minimize this effect. So this is a condition. And again, what we do is we look at the corresponding Newtonian method and get inspired by it to solve for to develop a stochastic approximation procedure. So the Newtonian procedure, as you know, is if this fxx is the Hessian matrix, and it has to be invertible, and this is the gradient vector, then this gives you, this recursion under all nice assumptions should converge to the minimum value if the minimum exists and things like that. And that suggests the corresponding procedure. So instead of this derivatives, we use the finite difference. So Cn is a finite difference interval, and we should, since it has to approximate the derivative, we make it converge to 0. And then this dfi x and Cn is the ith partial of f in the direction I. So we do it with f of xn plus Cn ei. Ei is the ith coordinate vector minus f of xn. This should be minus. That's a typo. So minus Cni, and correspondingly the yns, the difference in the y. So since you have to, you're trying to do the derivative, for each direction you must have two values of y. So if there are k, like the dimension is k, in each step you must have 2k many observations. So in n steps you must have 2k n many observations, and xi n is the, so you are trying, you are trying to measure this f of xn, f of x, the gradient of f at xn. So you replace it by the gradient of the y value, and difference between them will be the error, and that's what I am suggesting here, and that gives you the Kiefer-Wolfowitz procedure. So instead of the Hessian, you have some other constant an, and whereas you are supposed to look at the gradient, you can't do that. Instead, you should look at the gradient of the y, the difference in the y, along with some error. and study and try to solve, show that this thing here also xn converges to the required minimum. And also observe that if it's like if x are scalar and you are trying to find the minimum, then under all nice condition, what you are trying to do is you are trying to find out that f prime is 0. So you are that this Kiefer-Wolfowitz then kind of reduces to Robbins-Monroe problem with derivative of f instead of f. So that's why people refer to the Robbins-Monroe thing, because Kiefer-Wolfowitz, in a sense, becomes a particular case of Robbins-Monroe. So these are a few classical setup which developed and motivated the stochastic approximation. But before we go into the general model, or at least as general as we may require for our model, and try to analyze it and see the results, it's a good place to take a halt and check if there are any questions. Any questions?
Yes, do you have two questions? Would you like to answer now?
Yeah, sure.
Okay. So the one question is the first one. It's being asked that can you tell again the meaning of a weak convergence of probability measure in left shift interpolation? That is the first question.
Yeah. So maybe I'll not answer that right now, because we'll have a slide for that coming up when I'll be discussing that. Like the general model analysis. I'll remember this thing and I'll answer that in that setup. Yeah.
And there's the second question. Are Monte Carlo algorithm and Monte Carlo approximation related to each other?
Yes. So here I'm doing an approximation based on so Monte Carlo refers to something which are based on some random setup, and that's what we are doing it. So we are loosely, so it's a Monte Carlo algorithm, and since we are doing an approximation, so we are loosely using the word Monte Carlo approximation.
Till now, there is no further question.
Oh,
yeah,
okay.
This question's right there.
So let me try to go back to my shared screen, and my shared screen is visible, right?
Yes.
Yeah. So now let's look at the model. So this is the model that we have been talking about. So we have the evolution of x from xn to xn plus 1. We had this step size an, and then we had the actual process value, which is evaluated at xn, which is instead of f, now I'm writing h. One reason is I'm sort of using several of my past lectures and trying to put them together, so the notations are not necessarily very consistent, but from now on I'll try to stick to h, and the error which was xi now has become beta. But remember, it was an times h of xn plus, okay, it was minus, but you just changed the signs. It was f of xn minus xi n. Now I'm writing this h of xn plus beta. So that's my stochastic approximation equation. So we'll assume the xn to take a value in a bounded subset of R. The reason I'm trying to do that, as I suggested, I'll invoke some kind of a compactness argument. So it makes sense that we should stick to bounded. And as and when we'll apply it to the R model, we'll see that this boundedness will come in very naturally, because we'll be working with some probability. So we'll be inside a simplex. And we'll assume that this error term should go to 0. And as before, we shall take the step size to be positive, going to 0, and the sum diverges. Now, the crucial thing is that step size can be random. Now, when we are talking, we shall be looking two setups when things converge almost surely with or with probability 1, or the convergence is in probability. Now, when the convergence is almost sure, essentially you look at path by path, omega by omega. So for a given path, everything is deterministic. So this having random steps don't really make your problems any more or less difficult. But when you do convergence in probability, and I'll try to put up a screen and whiteboard and try to explain it over there. So there, the problem becomes a bit more challenging. In fact, a classical setup, they all take the step sizes to be non-random. And as I shall point out during when we go to this application to earn models, that the classically taking this, they take these step sizes to be constant. In fact, 1 over n. You know, like, I mean, if you take an to be 1, that's the most cardinal choice of an. If you take an to be 1 over n, then this condition is trivial, this condition is trivial, and that's also basic. So that's what they take. That works. But that works in a limited setup, and the calculations become quite terrible. But then there is a natural choice. 1 over n is not natural choice for step size in our model. There is another natural choice for step size. If you write down the equation, which we shall do next lecture, it's random. And there is a bit of challenge in showing all these three conditions for that. But once, if you can show this thing, and if you can push the analysis through, then it becomes much easier. But I mean, actually the differential equation becomes much easier. I'll discuss about that. But then working with a random step size there becomes much more challenging. And that was one of the contributions that we had in our 2019 work. And then this function h, which I was earlier calling f, we call it driving function, and we take them to be continuous. And so, as I suggested, the aim will be to embed this extends into a continuous time, a continuous process. So here now it's as a first step. What I do is we define Tn to be in the partial sums of the A's. And I didn't mention it, but T0 is 0, and this for n greater than equal to 1. And what I do is I now define so I have this pairs Tn xn. So at T0 is 0. So at 0, I have the value x0. This should have been a capital typo. This should have been a capital here. So the function x super 0 is nothing but the linear. So you have the points T0, x0, T1, x1, T2, x2, and so on. You have the linear interpolation of between them, and the linear interpolation is done on the entire real line. Observe that the sum of A's diverge. So Tn's will converge to infinity. So this, like, I mean, when you do this linear interpolation on the positive half line, you'll cover the entire thing. But there are no Tn's on the negative half line. So what I do is at 0, this gives you x0. So for all negative values, I need to make it continuous, so I make it constant at x0. And otherwise, I'm just again, sorry, this should have been capitals. So I just do the linear interpolation. So remember that Tn plus 1 minus Tn according to this formula is An. So this is clearly the when this is a linear interpolation when T lies between Tn and Tn plus 1. A simple formula. And this is a left shift. What I mean by left shift here. So by the way, this it's not an xn, all are random processes. So these are random. This is a continuous function on Rk valued continuous function on R. So it has so this is the answer to the question that was asked. So x0 is a continuous function, Rk valued continuous function on entire real line. So since it's random, it induces a probability measure. So that is the probability measure that we are talking about. And what is a left shift? So here is a left shift. So in x0, the value xn is taken at time tn. So what I'm trying to do for x super 1, I'm trying to make the function x super 1 be such that x sub 1 is taken at time 0. That's what I'm trying to do. Okay. So x1 at 0 is nothing but x0 plus t1, which is x0 at t1 is nothing but x1. So for x super 1 at time 0, I am getting the value x sub 1. X super 2 at time 0, I am getting the value x sub 2, and so on. So if you just fix your focus at time 0 and this super index run, then the functions will keep changing due to left shift, and these observations x sub 1, x sub 2, and so on, they will one after another keep appearing at time 0. So you can expect the behavior of this asymptotic behavior of the sequence of functions x super n at time 0 will give you the limit of the sequence x sub n. So this is what I mean by, in my case, is what I mean by left shift. So someone was asking what I mean by left shift. So this is what I precisely mean by left shift. And the reason I want to do the left shift, because I have this sequence of function. I'll let the function sequence run, but I will keep my focus only at time 0. And I'm constructing the function such that at time 0, I'll keep observing these x sub n's. And I'll be observing the x sub n's. Okay. So that's what I'm trying to do. Is the answer clear?
Yes, sir.
Okay. All right. Now, I'll also look at the error terms. So remember, at step n, a and bn is the error. So I look at the accumulated error and call it capital Bn. I think I used notation beta. Yeah. So this is the accumulated error, and again, like before, B super 0 is a linear interpolate of, oh, sorry, this should be Tn capital Bn. Tn capital B sub n. Okay, that's why I prefer to have something which I can edit, but that's not, I cannot share that, so you have to just bear with me. So this should be Bn. And again, here I will have the left shift, but earlier I am just shifting the t-axis from origin gets shifted to Tn. Here I am shifting the origin again to Tn, but I am also shifting the b-axis to 0. So here b0 Tn, so when you plug in t equal to 0, you should get b0 Tn. I'm subtracting that as well. So I'm shifting this point Tn as origin to this point Tn Bn. Okay, so I have these two linear interpolates. And with these two linear interpolates, so remember this was your original equation. And if you plug in this equation and do a little bit of analysis, so the function xn t will be xn 0 plus integral of this h of xns ds plus bnt. Now there will be an error term. Why there should be an error term? Because, you know, like, I mean, when I'm doing the original stochastic approximation, between the time Tn and Tn plus 1, this xns were staying constant. They are not changing. But here I am doing this linear approximation between xn and xn plus 1. So instead of a constant approximation interpolation, I am doing a linear interpolation, a continuous linear interpolation. So that will be creating some error, which I'll be calling ENT. You can write down the explicit notations for ENT, and actually you'll have to do the analysis. I'll not do that. I'll only write the notation BNT for you, and you will see that it's already quite scary. The purpose of writing BNT is not to scare you, but to point out what actually needs to be studied. So is the linear interpolation clear? And why I'm doing this? I'm getting that stochastic approximation equation into this integral equation. And I'll try to solve this integral equation. I'll first convert this integral equation to an ODE and solve for that ODE. Once you have this integral equation, what does it suggest to you? See, I mean, this En is an error term, so you would obviously try to kill this error term. Right? You want to make that sure that it's close to 0. Even this B and P, they come from some error, and anyway, it doesn't fit into this scheme of things. So you want to kill this B and P out as well. And if you drop these last two terms, what do you have? Xn t equal to xn 0. It's integral 0 to h of xns ts. Now, hold on for a second. Forget about all the randomness. So you have a sequence of functions, x super n's, and suppose x super n's converge. So x super n's converge to some function x. So I will get, you get xt equal to x. In all appropriate nice sense, it's in the space of continuous function. So assume everything, whatever you need to. So x super n t will converge to xt, x super n0 will converge to x0. And what will this integral converge to? This integral will converge to integral 0 to t h xs ts. H is continuous, and you have all nice convergence behavior and things like that. So hopefully you'll be able to show that. And so your integral equation in limit becomes xt equal to x0 times integral 0 to t h of xs ds, right? So that integral equation gives you a differential equation, which is nothing but x dot equal to h of x. And that is the ODE I'm talking about. I'm just speaking through it. I'll be showing it in the next few slides. So this is the integral equation. So suppose xn is relatively compact. Now, what is relative? Now this question about weak convergence comes in. So when we are talking about almost sure convergence, we'll be doing for each omega. So then xn will be some like sequence of continuous RK valued continuous function on real line, and the compactness is nothing but the thing that you discuss in the Arzelà-Ascoli sense. Okay, so because compactness for continuous functions are given by the Arzelà-Ascoli theorem, so it will be just that. But when xn's are when I'm talking about the convergence in probability, that's where the weak convergence comes in. So here these xn's are some random objects, continuous function valued random objects. So what do I mean by that? Let me see if I can use the whiteboard. I'm not sure how exactly it can be done. So let me try to explain it in words, and if it's not working, then I'll try to create a whiteboard and share it and see if it can be done. So you look at the space of all continuous functionals on space of continuous functions on R, RK valued. So these xk's are RK valued continuous functions on R. So you look at all continuous functionals on that. Take any such functional f, bounded continuous functionals on that. So take any such bounded continuous function f, and then you look at f of xn. So xn converges weakly means expectation of f of xn should converge to expectation of f of x for all bounded linear functionals f. All bounded continuous functionals on f. So is this statement clear? Someone who was asking about what should we mean by the weak convergence there? What we should do is we should look at all bounded continuous function from the space of continuous functions to real line. Take any such functional f, and xn will converge to x. The definition will be expectation of f of xn should be converging to expectation of f of x. Or if you are familiar with Wickster topology, this is nothing but the Wickster topology on the space of probability measures on continuous functions. I mean, these two definitions are same. I'm just spelling out the definition of Wickster topology. So Wickster topology, the probabilists are somehow drop the star, and we call it weak convergence, or topology of weak convergence, and not to be confused with weak topology. So it's actually the weak-stir topology. So is this clear?
Yeah, so this is similar like what you said, the convergence in the weak topology sense.
Convergence in weak-stir topology, not weak topology.
Okay.
Right, because space of probability measures is a dual of the continuous functions. So it's a dual space, so it should be the weak-stir topology.
Yeah, I got it.
Okay, so I mean, since it's a more mathematical audience, so that possibly is the right way to put it. Okay. So so if you have, so when I'm saying it's relatively compact in that weak-stir topology, or which we shall call topology of weak convergence. And if it's relatively compact, then it has a convergent subsequence. And similarly, we'll show that Bn and En are processes converging to 0. And all subsequential limit, as I was explaining, that these two terms will disappear, will satisfy x dot equal to h of x. And if we can show that this equation x dot equal to h of x has unique bounded solution, or unique solution in the correct domain, say Z, then obviously xn0 will converge to z0. But what is xn0? Again, there is a typo. Xn0 is nothing but this xn, because the way you have been defining this left shift was to make x super n0 to be nothing but x sub n. So that was the principle of stochastic approximation. So if you can write it down in the stochastic approximation form and then solve for this and show that this ODE has a unique solution, which is said, we'll be looking only at bounded solution. So Z is the unique bounded solution, then Xn will converge to Z of C. And actually what will happen is that what will happen is that the solution will be nothing but a constant function. So we'll be ending up solving for h of x equal to 0. So in the solution, Z will be a constant function. So x dot or Z dot will be 0. So we'll be solving h of x equal to 0. So the whole problem simplifies, as we shall illustrate day after tomorrow. And how do we do it? So the crucial idea is to look at these level crossing times. And these level crossing times are sort of the cardinal things studied in probability, mainly in martingale theory. So level crossing time starting at time n. So you look at an, and starting from an, you keep adding to it. That's how you get the tn's, right? And tn you start from a0. Here you are starting from level n or time n. So you keep adding to it, and you keep going until the time you just stay below t. So and call that t super tau super n of level t. So n is the index where you start, and t is the level you have to cross. So if you go one more step, you will cross level 1. And similarly, tau sub, instead of going, so this time you are going forward, m is greater than or equal to n, and this time you are going backward to gather, to gather just enough not to cross t. So how low you can go, and what can happen that you can get stuck at 0. But that will not happen, because eventually, as you can guess, you will let n go to infinity, So you will not go all the way to 0 because the sum diverges. So you will, given any finite level t, you will cross it. And then this function, the linear interpolate and left shift Bn can be written in terms. I'm not expecting you to read this crazy thing. Write it in terms of this tau super tau upper bar for t greater than equal to 0 and tau lower bar for t less than 0. Now these fractions, these are fractions between 0 and 1. They are given by the slope. So they can be easily managed. The problem that you will have to manage will be this thing, correspondingly this thing or correspondingly this thing. So these, what are these objects? These A and beta m's, what are these objects? They are nothing but, here you are studying from n going up to the forward level crossing time of and summing A and beta m. And here you are studying at n and going backward to the backward level crossing time, tau lower bar of A and beta m. So you have to somehow manage these sums and show that they go to 0. If these things go to 0, then anyway these things are 0. These things are bounded between 0 and 1. So you can show that the B and T, they will converge to 0 in the appropriate sup norm. It's not exactly a sup norm. It's uniform convergence on compact set, the corresponding norm. B and T will go to Bn will go to 0 in that norm, the norm of continuous functions on entire real life. Delayed sum should go to 0, as well as the backward delayed sum should go to 0. So when you are when we show almost everywhere convergence, we assume that it converges to 0 almost everywhere. When we show convergence in probability, we show that this converge, or we assume that this we make appropriate assumption to show that this converges in probability. Because that's natural. If you want to show almost everywhere convergence, you should assume, or intermediately you should show almost everywhere convergence, or for improbability, you should show improbability. So here is an almost sure case, xn bounded, taking value in S. This is a stochastic approximation equation. So what we assume that n is roughly like 1 over n, that is n times an as lim-inf strictly bigger than 0, and lim-sup strictly finite with probability 1. An goes to positive, an going to 0, and summation an diverges. So driving function, by the way, this driving function may be indexed by something random, because that will be important in our case. It should be continuous only in this parameter thing x. And this should have a unique solution, but it may depend on G. But for each G, it should be unique solution. Then, and for the error, so the crucial condition was this, the forward delayed sum and the backward delayed sum should converge to 0. For that, a sufficient condition is the errors beta, they should converge to 0 in Cesaro sense. That's kind of as the errors should be negligible. If the errors are not negligible, you are hopeless. We are requiring the errors to be negligible only in Cesaro sense. So it's as little as we can expect. And then using some Kushner-Clark, resolved by Kushner-Clark, sort of like a minor extension, we showed that xn will converge to ZG0 with probability 1, almost sure. And for convergence in probability case, what we can do is, we again start with the stochastic approximation equation. we have to make a few additional approximations. See, last time this HGX was required to be continuous only in this X parameter, but now it has to be jointly continuous in G and X. And the solution, last time we didn't, for each G we needed a unique solution, but now we need the unique solution to be continuous in G as well. And what we also have to assume, as before, that this forward level crossing error and the backward level crossing error both should go to 0 in probability. So last time in almost everywhere they have a nice sufficient condition that beta n, the C0 sums of beta n, that should go to 0 almost everywhere. That should give you that this errors should go to 0 almost everywhere. Here you do not have them. You have to show them directly, and that becomes a challenging task. And the result is that xn will converge to zg0 in probability. Actually, it will converge to 0 in first moment. That is, if you take their absolute difference and take expectation, that will go to 0. So crucial thing is here you have to make some more continuity assumption, which are not that difficult to check in the ARN model case. The maximum amount of trouble goes into checking these two error terms, the level crossing things, so to go to 0 in probability, because we don't have some, even if we assume n's are roughly like 1 over n, there are no nice sufficient condition in terms of convergence of beta n's like we had last time. Okay, so this is the theory of stochastic approximation that we shall require for discussing ARN models. So remember, this is the form of the stochastic approximation equation. The crucial thing is the differential equation you have to solve is x dot equal to hg of x. That must have a unique solution. The ans should be positive going to 0 and the sum should diverge. In almost everywhere case, the beta n's should go to 0 in C0 sense. For convergence in probability, you should have this error sums forward and backward, they must go to 0 in probability. Then you have the required result. So we have to mainly check three things: the property of the ans, that it's positive, which will be sort of obvious. It goes to 0, its sum is divergent. The way you do that is you essentially somehow manage to show that n is roughly of order of 1 by n in some sense. And challenge for almost everywhere the task is not difficult because you only show that bn's converge to 0 in C0. In probability case, convergence in probability, you have to show these two tough results. That's what we will do. Let's. So any questions here? Questions? No. So, Professor Ghosh, can you tell me how for the how much more time do I have?
Approximately 10 minutes.
10 minutes. Okay.
10 or 15 minutes. 15 minutes is okay, I think.
Okay. Okay.
Maybe we started 3 or 5 minutes later.
Okay. Okay. So no, I mean, this can be one good place to stop because I have explained stochastic approximation. And the other thing is I go into the next section, which I have already prepared, and introduce what ARN model is, and then discuss some results, and we'll pick up from there on Thursday. Thursday we are meeting, right?
Yeah, I think it's okay. Then we can have the platform of the discussion today now.
Yeah, okay. So either way, it's fine with me.
Yeah. Any question from the audience, from the participants? If they are having any question, then they can put forward.
Just I have one just query.
Mhm.
Is there any concept of right shift? You have done the left shift by.
Yeah, so if you do the right shift, the problem will be you'll be looking into the future.
Yeah.
And that you generally do not want to do. First of all, in our case, there is a purpose of doing this left shift. Because, you somehow want to keep your focus fixed at times, and then accents appear one after another. You want to sort of devise the system in such way that accents will appear one after another at times. So that's why we are doing the left shift, because we have put the accents at TNs, so we are bringing the TNs back. And so for this particular problem, right shift is not much useful. And in general, you also prefer left shifts, because for right shifts, you kind of tend to look into the future, which you do not want to do, because again, it doesn't make sense. So you'll be conditioning on whatever you know, and you do not want to condition on future, because that's not on your control.
Yeah. Okay, thank
you.
Yeah.
Yes, I do have one query. Am I audible?
Yeah, perfectly.
Yeah, the point is, suppose, let me just have this discussion over the, say, any kind of time series or signal. And I'm thinking of the errors, noises created at different levels. So in certain cases, what happens that, in the first or second observation, what kind of noise is being generated, that is somehow being propagated at the other levels.
Right.
So can we have any discussion over this propagation of the noise at different levels, this case?
I haven't really seen stochastic approximation being applied for time series, but as long as let me stop presenting, and oops, no, I shouldn't have done that. Let me see if I can bring back the presentation. Yeah, so as long as I can write it in this, you can write your equation in this form. And basically, you have to do three things. The step size should satisfy that it should go to 0, and sum should diverge. The beta ends, which we are doing almost everywhere, then the beta ends should go to 0 in Cesaro sense. And what I'm requiring is that the differential equation should have a unique solution, because then I'm getting a nice convergence result. But there are variants where the differential equation may not have unique solution. They may have different attractors for the corresponding dynamical system, and how does the corresponding stochastic approximation behaves? Those things are also analyzed. So a few good references for them will be one by a book by BUFLO, another book by Benaim, Benaim, another book by Vivek Bodkar. So those books will discuss those things as well. But I'll not get into that, because they are not important for the kind of art models that we'll be discussing.
Okay, I understand. Thank you.
Yeah.
Any further question from the participants? I have not seen any question further after these two questions in the chat box also. Yes, there is no such question. So in absence of any question, then let us thank Dr. Krishanu Moulik for his very wonderful and informative talk, I should say. And this is the first talk he has provided before us, and there will be one more talk day after tomorrow. And already, just for the participants, that I have already communicated the next 2 days program schedule with details to all of you by email, and please take your emails. And let me thank all the participants and the speakers also for today. And we are having some wonderful discussions right now. And tomorrow we will gather at exactly 5 p.m. Indian Standard Time. And again, we will be having 2 different talks tomorrow. So thank you very much. Thank you, the speaker. And thank you, everyone. So goodbye.
Thank you.
Thank you very much, sir.
Thank you. So we'll meet again on Thursday at 5. Thank
Yes,
you.
yes. Thank you.